Welcome. Today we're going to be looking at the notes worksheet entitled Verifying Trigonometric Identities Day 1. And this lesson actually represents a pretty dramatic shift in our curriculum. It's actually the beginning of an entirely different unit. And so what we're going to try to do today is kind of lay the foundation a little bit and show you what the expectations will be for the next few weeks. So I think what we'll do right away is start out with the little investigation that you see at the top. And let me go ahead and read it and have you think about it for a moment. And we'll write a few things in and kind of get everything taken care of. So it says, what is the fundamental difference between these two equations? So let's take a look here, everybody. On the left side of your page, you should see something that says 2x equals 4. And that is definitely an equation you've seen before. And then here's an equation over here, something like 2x equals x plus x. So there's some very, very big fundamental difference between those two types of equations. Obviously, both have variables, both have an equal sign, right in between. But really, what is the fundamental difference between the two? So I would argue that this is the one you've had the most exposure to right here, the 2x equals 4. You've been probably solving these now for several years. And what this is called is a conditional equation, meaning very simply that the equation is true only if x is equal to 2. That's it. If x is equal to any other number, it simply does not work. It is not a true mathematical sentence. So the equation is only true if x is equal to 2. And again, this is what is called a conditional equation. And there are all different types of families of conditional equations that you've been looking at and solving over the years, and that would certainly be one of them. All right, now we come over to the right side, and it says 2x equals x plus x. And I guess the argument can be made here then that the equation is true not just for a particular number or a couple numbers or whatever the case may be, but the equation is true for all real numbers. And so let's write that in there. So the equation is true for all real numbers. By definition, if you put any number in for the variable here on the left side and put that same number in for the variable on the right side, it would make a true mathematical statement. So let me make sure I have this correct for you on your paper. The equation is true for all real numbers, and everybody, this is what is called an identity equation. And as you can see from the title of the notes, of course, everybody, this is the type of equation that we're going to be dealing with at the beginning of this unit. So we're going to be creating mathematical trigonometric statements that are true for all real numbers. And so you know some of these intuitively. We've been kind of developing them over the course of the last several weeks here without really explicitly talking about it. But now what we're going to do is kind of get that out in the open. So there are a bunch, as you can see on your paper, that you're going to have to learn and know. And I hate to use the word memorize, but there are some you're going to have to utilize over the course of this unit. And so today is where we kind of started out here, get them all down on one paper, and then we'll go ahead and get a ton of practice with this. We're going to need it. There's some great math to be had here, and so let's see if we can develop it together. All right, so these are going to be what are called the fundamental identities, meaning, again, very simply, we're going to relate the 6 trigonometric functions together in some way, shape, or form, where if I put any number in for the variable, it would make the mathematical statement true. And so it's pretty fascinating stuff here in that we've been developing the 6 trigonometric functions over the last unit: sine, cosine, tangent, cosecant, secant, and cotangent. There happens to be dozens and dozens and dozens of relationships amongst those 6 trig functions. And so what this unit basically does is it offers us a way to explore those relationships a little bit. And so if you kind of think back to your geometry classes dealing with some geometric proofs, I guess the analogy can be along those lines, but what we're going to do is treat it in a slightly different fashion. So anyway, why don't we go ahead and start and lay some out here. We'll use the calculator to verify some of these as well if we have the opportunity, and then I'll show you what we're kind of looking for in terms of the verification piece. All right, well, let's start it out here, everyone. This is going to be what's called the reciprocal identities. And again, I think we've laid these out before. The relationships between. So cosecant, of course, is the reciprocal of sine. So for any number at all, 1 over sine of that number is the same as cosecant of that number. And again, I think we knew that intuitively. Almost from day one, we kind of set the precedent that cosecant and sine are reciprocals of one another. I think what I'll do is, we don't use this one quite as often, so I'm going to put it down on number 4, but essentially this would be the same as well. So 1 over cosecant is sine. So cosecant on the denominator is the same as sine in the numerator, and vice versa here. Sine in the denominator is the same as cosecant in the numerator. Okay, so those two pretty much go hand in hand here. You can pretty much guess the other 4 that are going to be in this category. So let's take a look at those. And so secant of x is going to be 1 over cosine of x. Again, for any real number, that is a true statement by definition. And then, of course, over here, don't see this one quite as often, but certainly if secant is in the denominator, that is the same as cosine in the numerator. Okay, so there are 4 of the 6 reciprocals, and of course the other pair that's coming together here. And we've actually seen a couple relationships between tangent and cotangent. So here's cotangent of x, and everyone, that would be the same as 1 over tangent of x. And over here, everybody, let's go ahead and just reverse it. So I'll do this as the number 6. And same premise, of course. When I see cotangent in the denominator, well, that is the same as having tangent in the numerator. So everyone, 6 reciprocal identity equations to kind of start it out here. And as I said, you can already see the ties between some of these 6 trig functions right here. Again, we kind of knew this to be the case. Cosecant and sine, we knew that relationship for any real number. And now what we're doing is just exploring that relationship in more detail. All right, the next one, of course, moving over to the right side of your paper, is what's called the quotient. Quotient, of course, means division. And so this is one that ties the primary 3 trigonometric functions together. It's kind of fascinating. Again, this is just an exploration of all the relationships amongst the 6 trig functions. And so here we've got one in a nice, simple mathematical statement with sine, cosine, and tangent. And it looks like this. So sine of x over cosine of x equals tangent of x. And again, I think potentially you've seen that idea before. You know, and I'm going to go ahead and explore this on the calculator momentarily. I would encourage you not to write this down. I'm just kind of thinking out loud with this. But I think you would know that to be the case because the sine ratio for any number, for any angle in radians, is the y over r. And the cosine value is, we all know, the x over r. And if I was to simplify that compound fraction there, as a matter of fact, the r's cancel, and I end up getting y over x, which of course is the tangent ratio. So as I said, these ratios right here sort of fit in line with the way our definitions have unfolded. And now we see really for any real number, the sine of that number divided by that cosine of that number is equal to the tangent of that number. So I'm going to erase this. Just wanted to kind of show you that piece very quickly. But I would encourage us, again, we're just going to do a lot of confirmation with this over the course of this unit. But let's go ahead and test it out. We have the calculator here. I would encourage you to do the same as well. It works in really degrees or radians, although really the argument can be made that we're talking about a real number. So I'm going to go radians on my calculator. And very simply, I'm going to do this, everyone. I'm just going to type in sine of any number at all. Hey, the first number I saw on the calculator was 2. So sine of 2 divided by cosine of 2. And there it is. That's what sine of 2 divided by cosine of 2 is. Now what I'm going to do, everybody, is take the tangent ratio of that same number, tangent ratio of 2, and notice it's the same. I'm hoping you tried 1 as well. And of course, what you saw is that the sine of any number divided by the cosine of that number is equal, of course, to the tangent of that number. Excellent. We're going to see that one a lot. Okay, and the other one would just be its reciprocal version, everybody. So if sine over cosine is tangent, then cosine over sine, everybody, should be cotangent, because tangent and cotangent are reciprocals. So if I flip this side, well, I have to flip this side. Excellent. All right, so as you can see already in this lesson, we've developed 8 identity equations. And as I said, I believe intuitively we probably knew these kind of going in, but we've never kind of written them out and explored them. Okay, let's go to my next board here. And these are the big ones, all right, what are called the Pythagoreans. So the Pythagorean identities, there are 3, which we're going to develop together here. Put a big asterisk, if you would, next to number 1. That is our ticket, everybody. And there are a couple ways to go ahead and develop this. I like the unit circle approach. I think it's a little quicker, a little more efficient. I also have done this in the past using a right triangle, hence the word Pythagorean, but it basically uses the same premise here. Again, this, in my opinion, is just it's slightly cleaner using the unit circle. Okay, everyone, so let's go ahead and try this out here. We're going to get used to a little bit of a different notation on this as well, by the way. And here's what I'm thinking. We've had a lot of experience with the unit circle now, so I just kind of posted one on your paper here. And basically, here's what I would argue. I have a right triangle within my unit circle. I'm going to label those 3 sides and apply the Pythagorean theorem. So everybody, let me start out with the easy one. As we all know, the radius, or the hypotenuse in this case, of that right triangle has to be exactly 1 because we're on the unit circle. So everyone put a little 1 in if you would. Okay, now, and I'm going to do this right here. In fact, I'm going to just call it theta. It could be any variable, quite frankly. I'm going to call that theta right in there. And very simply, I have the horizontal component and the vertical component to this right triangle. And so everybody, what I'm going to do is see if I can relate this horizontal component not just by using x. We all know that that is the x value from here to here, but in terms of our angle, in terms of our number right in here. And so if you remember correctly, the x-coordinate on the unit circle is the cosine ratio of our angle. So everyone, if you would, can you please just write in cosine of theta? Now again, we've defined sine and cosine and tangent a number of different ways based on different representations, but it did all start from this. And the unit circle tells us that the y-coordinate, again, on the unit circle, the y-coordinate is equal to the sine of theta. And so now, everyone, I have 3 sides labeled in my right triangle. I have the horizontal piece, I have the vertical piece, and I have the hypotenuse. And of course, if I apply the Pythagorean theorem, we could see that this squared plus this squared equals that squared. And everybody, that is our first one, and that's our big one. So we're going to read it as sine squared of theta plus cosine squared of theta equals 1. Now let's write that in, and I'll come back to exactly that piece momentarily. So this is how you're going to write it, everybody. And that's how I'm going to say it as well. Sine squared of theta plus cosine squared of theta equals 1. And you know what, actually, just kind of thinking about this, let me change it up just a little bit. Sorry about that. Let me just change one thing in terms of having it be as just any number, because that's what I want to keep it as just any generic number, and so I'm going to use my variable to represent it. So I'm going to do x there. Sorry about the change, just kind of thought of that off the cuff there. So sine squared of x plus cosine squared of x equals 1. Okay, so I kind of just use theta here as an angle, but again, theoretically, because it's in radians, it can just be any real number. And so as a result, to represent that, I'm just going to use the basic independent variable. All right, now, a couple things to note on that notation, of course. When I say sine squared of x, and please write this down, hopefully you have a little room here. What that means, everybody, is exactly the way we would think about it. It's the sine of x squared. So I take the side, which is sine of x, and I square it. We don't typically write it like this. We write it like this right here. They mean the exact same thing. And so sine squared of x really means sine of x squared. The ratio, the sine ratio of our number, we're going to square that. Please keep that in mind. We're definitely going to see that a lot. What it's not equal to, everybody, and let me go ahead and put a little symbol right there, it's not equal to this. It's not sine of x squared. So 1, where it's correct, everybody, this is the output, or the ratio squared. That's what it's equivalent to. This is saying it's the input, or the angle squared. And we're not squaring the angle, we're squaring the ratio. So just kind of keep that in mind. You can write it like this if you really want, but chances are you're going to see it more like this over here. Okay, so that's the big one, everyone. Sine squared of x plus cosine squared of x equals 1. Now, what I'm going to do is just bring my calculator up and actually verify that. And let's take a look. You guys do the same. So I'm going to turn this on here. And what I'm going to do, everybody, is do parentheses, sine, and I'm just going to pick any number at all. How about this? 4.1. So sine of 4.1, and I'm going to square it. Okay, so sine of our angle in radians, or sine of our number squared, and then plus, everybody, how about cosine of that same number? Again, same premise, everybody. Actually, you know what? Let me go back and insert just a little parenthesis right there. Not that I think it matters too much, but I just want to be clear on that piece. So cosine of 4.1, and let me throw a squared on that, everybody. And when I do, notice what it's equal to. So sine squared of any number plus cosine squared of any number is equal to 1. Absolutely. My hope is that you've thrown in a number on your calculator as well, different from mine, and of course you found that that's the same. And as you can see from the unit circle, that is the case. All right, now the other two, they certainly come up quite a bit, not certainly as often as a sine squared plus cosine squared equals 1, but they do come up quite a bit. As a matter of fact, just kind of looking at my board here and your paper, I'm going to hold off on 2 and 3 for just a moment. As it says on your paper, everybody, does everyone see this? Variations on 1. Well, that sine squared plus cosine squared equals 1, we're going to see that in that exact form. What we also do is we also see it in a slightly modified version. So I want you to be able to recognize these as well. If I bring over the cosine squared of x just to the other side here, 1 minus cosine squared, as you can see, would be equal to sine squared. So that variation does come up quite a bit. It's obviously the exact same thing as number 1, just written in a slightly different way. And by the same token, everybody, I could have taken my original and I could have brought this over to the other side. And as a result, we would say 1 minus sine squared equals cosine squared. Okay, so those are the two that we would go ahead and play out. We do have to be careful about a couple things here. And again, you can write this stuff on your paper or not write this stuff on your paper. The relationship between sine and cosine are two primary trigonometric functions. The ones that we did the most work with over the course of this last unit has a beautiful connection right here. Sine squared plus cosine squared equals 1. Okay, what we have to be careful of is how to use it. So for example, I've seen students over the years try stuff like this, that if sine and cosine would be tied together on the squareds, then they're also tied together just as is right up here. 1 minus sine is equal to cosine. Well, let's go ahead and see that and see if that is true. So again, guys, just trying to help out with what I've seen in the past and what you need to be careful on. So I'm going to do this, just 1 minus sine of 5. Get an answer. And then I'm going to do cosine of 5, and I'm going to get an answer. And notice, everybody, they're different. They're different. So sine and cosine are tied on the squareds. Please be very, very careful with that piece. Sine and cosine are not tied together this way. This is not a true mathematical sentence right here. So I am going to delete it out of existence, and you are going to make sure that you never do that. Okay, so 1 minus cosine squared is the same as sine squared. And again, it just comes from this, which we confirmed on the calculator as I just picked any random number, and it worked. Okay, everyone. So what we're going to do is get these other two going, write out a couple more things, and then the developmental process will be taken care of, and then the concept of what we're looking for here today will sort of take hold in just a little bit. Okay, so let's take a look, everyone. Here's what I'm going to have you do on your paper. Can you please write sine squared plus cosine squared equals 1. So there, as I said, is a great connection between our primary two trigonometric functions, sine and cosine. That is the best tie-in between the two. Now what I'm going to do, guys, is see another connection between another two out of the 6 trig functions on the squares. And so here's what I'm thinking, everyone. If you would, divide the entire left-hand side by cosine squared. And of course, as an equation, everybody, whatever I do to the left side of the equation, I am going to obviously balance with the right side. Now, as I look at this, everyone, this piece right here, or I should say this cosine squared of x, is a common denominator. It's a fraction, everybody, and it is a common denominator to this and to this. And so what we're going to do is kind of split this apart and apply this cosine squared to both of these, to that one and that one. And so I guess I would ask you this. What is sine squared over cosine squared, everybody? Look up above at the quotient one, and sine over cosine, in this case on the squareds, that's okay. Sine over cosine is tangent, so sine squared over cosine squared happens to be tangent squared. So I have tangent squared of x plus, and then I'm going to put a plus right here, everybody. This cosine squared also goes with this. So what is this, as a matter of fact? What is cosine squared over cosine squared? It's 1. Anything divided by itself is 1. Now, everybody, look at the top left of your paper. What is 1 over cosine squared? These two go nicely together as a reciprocal. On the squareds, that's okay. And, of course, 1 over cosine is secant. So 1 over cosine squared is secant squared. And so, as I said, sine and cosine tied at the hip on the squares. Tangent and secant, again, tied at the hip on the squares. Tangent squared of x plus 1 is equal to secant squared of x. All right, beautiful. I'm going to bring my calculator up to verify exactly that piece. If you want to do the same, that's great. So I'm just going to do tangent of any number. I'm going to do tangent of 9. And let's see, I'm going to square that plus 1. So tangent squared of x plus 1. And I get that right there, of course. And now what I'm going to do, everybody, is the secant squared. So I'm going to do 1 divided by, and let me make sure I've got that right. So cosine of 9, and let's see, let's square that, everybody. So tangent squared of 9 plus 1 is this right here. 1 over cosine of 9 squared, as you can see, is the same number. Okay, so number 2 in the Pythagoreans taken care of. Let's go get number 3. And I'm going to come right here on my board. You guys do what you want, where you have a shot. So we're going to use the biggie to get the 3rd. Here we go. So if you remember what I did to get number 2, I'm going to do something very similar. Instead of dividing by cosine squared, everybody, I'm going to divide by sine squared. So we see the last 2 out of our 6 trigonometric functions connected through these Pythagorean identities here in just a sec. So this, everybody, is what's called a common denominator to this term and to this term right here. So sine squared over sine squared, everybody, is 1. Cosine squared over sine squared, everybody. Look at the quotient one at the top. Cosine over sine is cotangent, so cosine squared over sine squared is cotangent squared. And I would ask you this, of course, what is 1 over sine squared? And if you look at the reciprocals at the top, should be cosecant squared. And there ties the last 2 together using the Pythagoreans. So sine and cosine, tangent and secant, and everybody, of course, now cotangent and cosecant for any real number in existence. Put that in for the variable, and the equation is true. Okay. It is a lot to process. I certainly know that, and we're going to take the time to develop it. That's not a problem. I'll kind of show you where these problems are leading in just a little bit, but you really have to know these pretty well. The reciprocals, the quotients, and especially the Pythagoreans. And as I said, put an asterisk next to number 1. That's the biggie. Okay, even odds don't come up a ton, and we didn't talk too much about even odds. It's really just talking about inputs and outputs, the opposites essentially, the negatives. So I'm going to put them in. We'll see them once or twice. In terms of memorization and really utilizing them, I would argue that if you know the reciprocals and you know the quotients and you really know the Pythagoreans, I won't hold you too accountable for these right here. So it's just inputs and outputs dealing with the opposite symbol. I might verify one just very quickly. And again, I think we might have known a few of these intuitively. And I'll just kind of write down a couple things because I didn't really explore these in great detail as we went through Unit 4. But essentially, this would be an odd function. Sine is what's called an odd function, and this would be the rule for an odd function. The sign of the opposite of the input is equal to the opposite of the sign of that output of the original input. So anyway, sine of negative x equals negative sine of x. Again, cosine happens to be even, and so what that means is the cosine of negative x is actually still equal to the cosine of x. And again, if you actually pictured the unit circle, you would probably know this to be the case. We saw some negative inputs, and again, we didn't really explore this in great detail, but these would be the cases. Tangent is what's called an odd function, and so it has the same rule as sine. And so tangent of negative x, negative tangent of x. And the reciprocals would be the same, of course. So I doubt we will ever see the secondary ones here with these even odds. But this would also be an odd, by the way. And so you get this piece. And let's see, secant would be even. And last but not least, everybody, cotangent would be odd. Okay, good. And again, I just figured I would go ahead and grab a calculator and just show you what that means. Not too big of a deal. So sine of the negative, so here's what I'll do. How about I start with an input of, 3. So I'll do sine of negative 3 and get an answer. And then what I'm going to do, everybody, is the opposite sine of 3. And as you can see, I get the same answer. So taking the sign of the opposite input is the same as the opposite of the output. And let's do cosine. Do the same input, what the heck. So this one is basically saying that the cosine of negative 3 is actually the same as the cosine of 3. Let's take a look. And there you go. So the input, changing it from its opposite, gives us the same result. Again, not a big deal. Don't stress too much about those. The other ones up above are the ones you're really going to focus in on. So we have taken a lot of time to develop these relationships, and that's what I said. It is really just an exploration of the relationships among the 6 trig functions. And what we're going to do is explore dozens and dozens of them using this piece right here. So this is what's called verifying trigonometric identities, and as it says on your paper, we are going to very simply show that one side of the identity can be simplified so that it's identical to the other side. Now there's a little asterisk and a few lines right here, so bear with me on this. We're going to put a few things into the mix right here, and then I'll just give a quick verbal explanation before we try a couple ideas out. So we have to be careful. We do have to change our mindset here, and it's almost like a little paradox on this. So let me be very clear about how these equations are. They are not like those conditional equations that you've been working on for the last several years. So we are going to have to change the training, basically. So not like conditional equations. And if you remember conditional equations, you've been basically trained. Let me just make sure I write it down as I say it here, where we perform the same algebraic steps to both sides of the equation. So if you remember, every conditional equation you've done, you've always kind of done one thing to one side, and then you've had to keep it in balance, and you've done the same thing to the other side. These are different. You are going to verify that the equation is true. And so what we need to be careful of, let me again write it down, and then I guess I'll do my verbal explanation after. If you do this, so if you treat it like a conditional equation, you're assuming something is true before you've proven it true. It's kind of a catch-22 there. So you assume the identity is true. Okay, so you assume the identity is true before you've verified it, before you've proven it to be true. All right, let's get that in there, and we'll kind of talk about how this plays out. So before you have proven it to be true. So verifying these identities, everybody, is like a proof. And so what we're going to do is prove that one side of the equation is the same as the other side of the equation. The analogy I like to use is the other side of the equation is like the answer in the back of the book. You can't use it. It's there. You know what it is, but you can't use it. You're trying to get to the answer. So think of it that way. One side of the equation is what you're working on. The other side of the equation is the answer in the back of the book. I know what the answer is. I just can't use the answer. Because if I use the answer, I have something like this right here. I have a little paradox. So if I do something to both sides of the equation, I'm assuming the equation is true before I have proven that it's true. And I can't do that very simply. Okay? So just the best way to describe it is that the other side is the answer in the back of the book. You know what it is, but you can't use it. Okay? So let's try it out here. First one, it says verify the identity, and please, everybody, it just helps me see your work. Work vertically. Don't go all over the paper here. It would be impossible for me to follow it, and please don't do that to me. So work vertically. You're going to pick one side of the equation, and you're just going to work with that, and then you're going to make it look like the other side. So here's what we're going to do. We're going to talk strategies in just a little bit. But for right now, the first one, let's just kind of start it out here. This is a mathematical relationship among 3 out of our 6 functions. So it's basically saying the secant of any number times the cotangent of that same number is equivalent to the cosecant of that number as well. Okay, so we have just, again, it's just a relationship among 3 out of our 6. We are going to prove that this is true. We're definitely going to confirm it on the calculator in just a little bit, but let's prove mathematically that it's true. And so here's how it works, everybody. I'm going to take the left-hand side of the equation, and I'm going to play around with that using identities and using algebra to make it look like the right-hand side. I'm not going to mess with the right-hand side, everybody. That's the answer in the back of the book. So here we go. What do I know about secant? Well, everybody, I know that secant for any number in existence is 1 over cosine. And so what you're going to do, you're going to change, using an identity that we know, you're going to change secant of x to 1 over cosine of x. All right. Now, everybody, let's use an identity, of course, for cotangent of x. What do we know about cotangent of x? Well, we know 2 things. And so we're going to have to make a decision here as to which is the better. I know that cotangent, from the quotient standpoint, is cosine over sine. And I know that cotangent is also 1 over tangent. Well, again, let's be logical about this. If I have a cosine here, it wouldn't be a bad idea to utilize the one that has cosine in this one. So what I'm thinking, everybody, is let's use the quotient one. And so cotangent, everybody, is cosine over sine for any real number. And now what we've done is we've created 2 fractions side by side, separated by multiplication. And how do I deal with multiplication? Well, everyone, I can cross-cancel. As we all know, cosines would cancel, 1 in the numerator, 1 in the denominator. And if I cancel those out and then push everything across and multiply them together, I end up getting 1 over sine of x. Okay, so utilized identities, one here and one here, then utilized just a little middle school algebra, canceled those out, and now I'm left with this. And everybody, if you look at the front side, or if you see this right here, this should really ring true. What is 1 over sine of x? It's cosecant of x. And that's it. Now if you take a look, everybody, there it is. And so here's what I'd encourage you to do. This is just my thing. Only at this stage, I would bring down the other side, and I put a little check mark above it. You've shown that that's the case. Now you've proven it's true. Okay. Just due to the time, I won't go ahead and throw in a number here. Maybe on the next notes worksheet, we'll do exactly that. But essentially, if you put any number in for x here, what we've shown is mathematically that's equal to this side right here. And that's how they're going to work. Please, everybody, in terms of your format, notice I worked vertically. 1, 2, 3, right on down. And I got it to work. Okay, so that is how these are going to play out. From easy to hard, that's how they're going to work. Okay, so obviously, I want to give you a few strategies, a few ideas here. And so let's do this. Strategies for verifying identities. What I would say is, generally speaking, you want to start with the more complicated side and transform it to the simpler side. Most definitely. You'll hear me use this phrase a lot as I'm helping you with these. You want to break the expression down, not build it up. It's easier to simplify things mathematically than to make them more complicated. So break them down, don't build up. That's sort of the layman's terms what that would be. So start with the more complicated side and make it simpler. Okay, use identities, of course. You saw what we did. We changed secant to 1 over cosine, absolutely. So use identities written in a different way. We kind of talked about this on the front side, but sine squared of x, this one just comes up a lot. That's why I just want to be sure that I've covered my bases. So that one comes up as is. You'll see a lot of sine squared plus cosine squared. And that is just 1, as a matter of fact. So I'm going to write it like this, but again, we saw the variations before. So something like, oh, if I see 1 minus cosine squared, which I will see a lot, that's equal to sine squared. Or if I see 1 minus sine squared, that's equal to cosine squared. So you're going to have to recognize them. Absolutely. Number 3 on your paper, lots of algebra with this. This is really a great way to solidify some of those algebra skills from first semester. All of that is going to come up with a vengeance here. There's a lot of factoring in this. And as you even saw just on that basic first problem we did, that example 1, lots and lots and lots of fractions. Oh, goodness. So multiplying fractions, adding and subtracting fractions, working in what's called compound fractions, if you remember that from first semester. All of that is definitely going to be part of this. I would do this a lot. When all else fails, if we don't see anything right away, try to express everything in terms of sine and cosine. All of the other 4 trig functions have a reference to sine and cosine. So either with the quotients or the reciprocals, you can change any one of the other 4 to sines and cosines. And we're going to do that a lot. That's actually a huge strategy. And then number 5, everybody. At each step, keep in mind the expression on the other side. The analogy I use for this, everybody, is it's kind of like chess. Now, I'm terrible at chess, but I respect those who can play, because what they can do is they can literally see several steps out how the board will progress from one move to the next to the next. And that's what you're going to be able to do with these. You're going to be able to see the answer on the other side, basically what you're going for. And as you get good at this, you're going to be able to see the progression from one step to the next to the next. And you're going to get some good experience watching that unfold. So it's very much like chess. Okay. If you like puzzles, you might really enjoy some of these problems. I think they work out quite nicely. And if you don't, if this is not your favorite thing, it's okay. Work through it as best as possible. I will help you as much as I possibly can, and I promise you will improve. You will get better and better at these as you practice. Well, let's round this out here. It's been a rather lengthy lesson because it does take a lot to develop, but I would love to do examples 2 and 3 and then give you some time to, practice on your own. There's going to be ample time to work through some stuff, so work with other people on these too. Okay. Well, everyone, this right here. So I'm going to change this side, and I'm going to make it look like this side. So that's my answer in the back of the book, everybody. So I have cosine of x. I have cosine of x times sine squared of x. I can work with that a little bit. But what we want to think about is what can we do either algebraically or with an identity to go from here to here. Now, one thing that comes up a lot with these is you will notice on the left-hand side of the equation there's a minus. And on the right-hand side of the equation there's no minus. It disappeared. Generally speaking, there are only a couple ways that can work out. I would argue the one algebraic way that works out, everybody, is through the idea of factoring. And so what I'm going to encourage us to do is take a look at these two terms separated by the minus, and you tell me what the greatest common factor is. And I'm hoping you would agree with me that the greatest common factor, what can be pulled out, everybody, is cosine of x. And so that's what I'm going to do. I'm going to pull out a cosine of x. And when I do that, I get that right there. Now, cosine of x as a factor, it's great. There's really not much I can do with it. My hope is that the light goes on for you. This you have to recognize. I'm afraid there aren't too many ways around it, so I've been trying to emphasize that all lesson. What is 1 minus sine squared? Well, by definition, from our Pythagoreans, everybody, oops, sorry, I missed that. Let me quickly fix. By definition, 1 minus sine squared is cosine squared. So what we do is we literally replace, as an identity, cosine squared in place of 1 minus sine squared. And now, once we saw that, and again, you sort of knew this had to happen, right? Hey, everyone, there's only cosine on the other side. So how am I going to go from sine to cosine? That's our relationship right here, everybody. 1 minus sine squared is cosine squared. And then, of course, what is cosine times cosine squared? It's cosine cubed. Excuse me. And there we have it. So I do that, I don't know, just helps me orient myself and say, okay, I've succeeded. I have verified the equation to be true. Notice I did not bring this down until the very end after I figured out that that's what it's equal to. Okay, last one here of this notes worksheet. Look at this one. This is a nice one. Remember, we've explored 6 trig functions in the last unit. Here is a great relationship amongst 4 of them: sine, tangent, cotangent, and secant. For any real number, this mathematical relationship is true. Well, let's verify it. So it depends on what we want to do here. I would start with just saying that's sine of x, and there's not much I can do. Now this one, we have a couple different options, but I'm sort of seeing this as one of the strategies we want to do is really employ sines and cosines as much as possible. Because if we can figure out everything in terms of sine and cosine, then we can apply our algebra and simplify properly. So tangent, as we saw, is sine over cosine. And cotangent, everybody, is cosine over sine. Now, I'm not saying that happens all the time where you would change it to exactly what I have on the board, but I would say more often than not that's a good strategy. Again, I think I wrote that number 4 on your sheet. Change things to sine and cosine and see what happens. Now, we have a couple options. We can either add these 2 fractions together here, or we can distribute. It's up to you. If you pursue a different path than what I do here, that's perfectly fine. But I'm going to distribute the sine of x inside to those parentheses. I'm going to distribute it. And I sort of see this, everybody, as sine times sine over cosine. So when I do this first piece, everybody, I get sine squared over cosine of x. Hope everybody sees that. Think of this almost as like a sine of x over 1. So multiply the numerator, get that. 1 times cosine, get that. Now everybody, when I distribute it into the second fraction there, I have a sign on the numerator and a sign on the denominator. Everybody, what happens to those? Well, they cancel. And so they cancel, and I'm left with cosine of x. Now, because this is a fraction here, I'm going to put this as just over 1 for right now. You don't have to, but I'm going to do that just for my visual perspective. Now, here's what I would argue, of course. There is a plus on the left-hand side of the equation. Everybody, is there a plus on the right-hand side of the equation? No. So does that pretty much tell us that we're probably going to want to combine these two fractions together? Yeah, of course. And so you're going to do a lot of this. So I'm hoping you remember how to add and subtract fractions. In this case, everybody, we're going to add fractions together by getting a common denominator. So the common denominator for cosine of x and 1 is cosine of x. So however we change the denominator of each of these fractions, we're going to change the numerator in the same way. So I'm hoping everybody agrees with me that the denominator from here to here has not changed, and so the numerator doesn't change. So I get sine squared of x. Now everybody, how did the denominator change from here to here? It was 1, and now it's cosine of x. It looks like I multiplied this by cosine of x to get to here. So if I multiplied the denominator by cosine of x, what do I have to do to the numerator? I have to multiply by cosine of x. And I end up getting cosine squared. Now again, this I can't help with. But you have to be able to recognize this piece up here. And as we saw, we took a lot of time to develop it. Sine squared plus cosine squared is 1 by definition. So that whole numerator is just 1. And so I get 1 over cosine of x. And by the way, everybody, what is 1 over cosine of x? Look at the right-hand side, and that's exactly what we wanted. And that's how it's going to work. Notice my work, everybody. I just vertically on down, simplify, used identities, did good algebra, and it's equal to the right side. And you've proved it. Okay, so this obviously was a rather lengthy lesson here. There is some wonderful material in here. And as I said, it's an exploration. That's really all it is. Some very good theoretical math, just relating the 6 trigonometric functions together in a variety of ways. So get practice on it, please. We will practice more together, of course, and help each other out. I can't stress that enough. Okay, well, thank you very much for listening. I appreciate it. And you will let me know any questions that you have.